Um, and yeah, so just to give you all an introduction, Ravemba is a Google developer expert and a researcher at Rice University in Texas. Ravimba, why don't you tell us a bit more about what you do and your areas of expertise?
Yeah, thanks, An, for the introduction. Hi everyone, I'm Ravimbo. Today we're going to talk about turbocharging web apps. A little bit about me. So, I'm a Google developer expert in AI and ML and also web, and also a cloud champions innovator and a research innovator. I'm also a PhD student, and some of the work I am going to talk about today slightly relates to what I do, but mostly it's my GD activities. So, with that, uh, today we are going to talk about turbocharging web apps, or more specifically, AI apps. Now, what does web app mean, or like web AI app means? Like, what are we going to talk about? Is it like just AI models? Most of the AI models we have played is probably through websites, but probably is not a web app if we really talk about it. My focus, complete focus in today's talk, and everything will be able to run machine learning faster and consuming less power on device, on your own devices. So we need to be able to run this directly on your browser without going through any extra hoops, installing anything else. That, apart from giving you freedom of platform, also give you model portability. What does it mean? We'll talk about it later. And one of the key things we are going to talk about here is the technology, the web, the AI stack that will enable us to run these heavy machine learning models efficiently in your browser. If you want to build an application for your users, which can be accessed by thousands or millions of people, you have to be also aware of the kind of different kind of devices they are using and how your application will perform based on them. So efficiency is a very big thing, and we're going to talk about the different nitty-gritties of what enables this stack, and also some of the efficient, like performance tricks or efficiency tricks of that you can use. One of them is how you can cache your models. So let's start with an introduction. We have all heard the story. AI is transforming the way we interact with technology. The web is no exception. This year, Chrome added generative AI features, including creating custom themes. Some of you who might have installed Chrome new or just updated the Chrome will get this introduction page where it will tell you that, okay, you can create your own theme using AI. Those are the nice little tricks, but it can do much more. So AI can enrich web applications themselves. So today, a web page like this slide can embed intelligent components for vision, like picking out faces, recognizing gestures. So, for example, if we use Google Meet now, or if you use any other video application, video chat application, you will see some of them have these features where you do certain gestures and it will give you thumbs up, thumbs down, certain features. Those kind of stuff you can build on yourself as well. So some of those even more advanced things we can implement directly on browsers now, and we'll see how this technology enables that. So why is this powerful? Now there are several reasons, and I'll talk about some of the important ones. The first one, that which is very important from a lot of us while building applications, is reducing server cost. Whenever you are running any model, like example GPT or Gemini or anything, that's gonna run in either of the two ways. One, you are going for specific models like Gemini or GPT, which are hosted commercial models, and you hit a API, you get a response back, just a normal web application. That means you have a server where it's running, and mostly it's a hosted server. So you pay for the API cost. If you have millions and billions of users, that API cost is going to add up very soon. Uh, Also, if you have your own open source models running on your own stack, that technically is free, but running in the stack is not. So you have to keep a infrastructure running where it's going on inferencing again and again, and that adds a significant infrastructure cost very soon. Running in web is interesting because it runs on your user's machine. So you don't incur the cost, you pass it on based on what a user actually uses or not. For applications that are particularly sensitive to latency, like audio or video application, having all the processing happen on device literally reduces latency. For example, look at this video right now, while we are doing this through Bevi, or even if you have a Google Meet, you see my background, which shows my very messy room, is kind of blurred. This is running directly on my device. So this blur is getting produced right now on my device, and then that video is transmitted. So this on device segmentation model is running directly on the browser. This is very important because if you have to build an application like that and you have to have a server where it runs, you are going to incur very much cost, and also it's going to introduce a lot of latency. Running on the client side also has potential of unlocking new class of application that requires increased privacy, where data cannot and sometimes should not be sent to the server. One of the example is, of course, the video, but there are much bigger applications, as we will see. Now, let's take a step back to understand how AI workloads can run on web today. So this is a very kind of like stack, how we are gonna see and run the applications today. Now, this is where we stand, application developers and researchers that build and train the models. And either it can be you, or you can be using some pre-trained model where you don't have to train the model, you just know this model does something and you just want to run it. So once you have that, you execute it in the browser. So there are a couple of ways of doing that. Each of these in this stack are runtimes. So for example, you can use runtimes like TensorFlow.js, Onyx, Web, or MediaPipe. And these runtimes makes use of web APIs for execution. Today, some of the demos we're going to see, I'm going to use mostly MediaPipe, but I'll also show some of the TensorFlow.js examples, but I'll also give you a link where you can just play with them. Now, all these runtimes eventually bottom out into running on the CPU through JavaScript or WebAssembly, which is awesome, which might still not be performant enough. We want the applications to be very performant. So if our user has a GPU, we can also pass some of these through web GPU. So we are here to talk about how WebAssembly and web GPU are evolving to make AI and machine learning workloads run better and faster, and run some of the bigger AI workloads which were not previously possible to run just through JavaScript and CPU. So this is a transformer stack. If you just look at it, so machine learning workloads push tensors through a graph of computational nodes. These tensors, which are essentially multidimensional array of numbers. So just imagine they are array of numbers. They are inputs and outputs of these nodes, which performs a very large number of computation. Now, if we look at it, some of the aspects which are important is that these tensors are huge. By huge means there are hundreds or thousands of elements or more. Imagine an array of like thousands of elements or more. And can we introduce more, or there will be a lot of parallelism involved here, because often the same arithmetic operations are done across all elements of like all elements in that tensor. And finally, machine learning doesn't need a lot of precision. So a lot of the models, when you open source models, when you look at it, you will see that they come with some of the suffixes like Q8, Q4, K underscore M, something like that, FP16, uh, some things like that, right? So these are floating point numbers, these are quantization numbers, and we will essentially use these three aspects to kind of exploit how to run these much faster in our devices. So some of the things we already get advantage is that fortunately, since designers have started to pick up on these, that's why you have the NPUs and stuff coming up uh, to make these models run faster. And we will use WebAssembly and Web GPU to kind of exploit some of these in today's talk. So we should still add here that if you're a web application developer, you are unlikely to use these new low-level primitives frequently, but that still doesn't hurt you because you can still utilize them. So we expect the tool chains and frameworks that are being built to used to build these applications to actually integrate these benefits directly to the tool chain, so that even though you know in today's talk what is going on inside, you essentially don't have to implement them by code. But if you are somebody who is not only a web developer but also trying to get handy with tuning models, specifically hand tuning applications for performance, or you are somebody who is working to squeeze out that last part from your web applications, then these features will be directly relevant to you because you are not bounded to whatever the toolchain makers or the JavaScript framework you depend on, or the other frameworks you depend on, whatever they implement. So let's talk about the WebAssembly first. So, what is WebAssembly? I want to make it more a little bit interactive. So, yes, there is the option of raising hands. So, how many of you have heard about WebAssembly? Just raise your hands. We'll just see a like show of hands.
Did you ask heard of or used?
Heard. Okay. Okay, in that case, let's go deep into it. So, what WebAssembly is it's a compact bytecode format that runtimes can understand and execute. Uh, Imagine that as a kind of black box where you can have your C++ code directly converted to a WebAssembly rather blob like a black box, which the browser actually can understand and execute very efficiently natively, not in Java, not like JavaScript. So it is designed to take advantage of the underlying hardware capability. So it can execute in native speeds or very near to native speed. So this will be almost like writing a C++ code. And also this is validated and it is executed in a sandbox environment. So you just cannot have a code just like crash your browser. So it does give you the guarantees. Now, there are things called WebAssembly modules. The modules are information represented using a dense binary encoding where we can have our information, like our codes. So compared to a normal textual format, this will be in a very efficient, faster format, which is not human readable, but very fast for decoding, and that reduces the memory usage. Now, these specifications we talk about, they are getting changed all the time. This is an open W3C specification, but almost most of the stable ones are already in almost all the browsers you use it. So, for example, Chrome, Firefox, anything that builds on Chromium, so that means Edge, Brave, Opera, Vivaldi, and also Mozilla Firefox Gecko has its own implementation on most of the WebAssembly formats, and Mozilla is one of the like huge party who proposes formats as well. So the binary format, the plus point is that it doesn't make assumptions about the host environment. So it's designed to work well with non-web embeddings as well. So essentially, there is a Rust. If you specifically for Rust, if you just look, most of the things which we run in WebAssembly, including WebGPU code, there are Rust for models which can utilize that. Now, the thing I want to emphasize is that when you have an application that you are porting to WebAssembly, it can be compiled once and run everywhere, be that a desktop, laptop, or phone, or any device that a browser runtime can be run on. So any device where a browser is running and has support for its APIs, it can be done. So which probably means your very advanced car with a browser. So while the rest of the talk will be focused on the features, you can kind of like look around what else WebAssembly can enable for you. Now, most production applications that runs AI inference on web today make use of WebAssembly, both for CPU and GPU compute. Let's talk a little bit about more how compute on native platforms and web can be different, because that will change a lot of decisions we make while making the like while building web applications. So on native application, you have full access to both general purpose and special purpose compute, which essentially means you have access to both your CPU and GPU directly without any effort. On the web, that's not always the case. On your browser, for portability and security, you carefully have to, or the browser carefully evaluates what set of primitives are exposed to the web. Hence, to kind of balance the accessibility and the security and the performance. So when you build an application using AI or any of the web GPU API, you have to be careful about what is available to your application. And that will completely vary based on who is running in the application. So what WebAssembly does is a portable abstraction for CPU as well. So all the WASM inferences is run on the CPU. It's definitely not most performant, but CPUs are all ubiquitous. So any person who is running your application, they have a CPU. So you can be completely sure your code runs everywhere, but that's also good and bad. You have to be very careful when you are building an application to check what compute availability is that code is running on. Based on that, you might want to disable certain instructions. So, for example, some of the examples where you already see this. So, Adobe most recently used the TensorFlow.js version WebAssembly backend to enhance Photoshop for the web. If any of you is using Photoshop and you use the light version in the web, most of the effects and everything that you use there very fast, very performant way is essentially using TensorFlow.js backend to accelerate that. Google Meet's background blur was one of the early implementations of Wasm-based video effects, and then there are a lot of very interesting things. So YouTube's AR effect, Google Photos web editing part, they're all great examples of how some of these are implemented. Apart from this, there is a lot of very interesting demos by community using tools like Llama CPP and Whisper Tiny. These models are now the Whisper Tiny models are now good enough to actually run directly on your computer, on your browser, without running it in any server or getting access to any information, and it runs perfectly fine. So these are some of the applications which are already happening. So if you go to MediaPipe Studio, if you just Google on the left, there are a lot of these examples already available where you can just play with them. And you will see almost all of you are able to run this on your laptop right now without having to worry about if you have a GPU or CPU. So that's a huge win for the web, because previously, a lot of these things were not able to run in a performant or in a reasonable amount of way without you having a GPU backend and without people having to write very specific codes for very specific platforms. I'm not going to go for these demos because you can just try them yourself right now from MediaPipe Studio. Now, when it comes to ML workloads, we are continuing to listen to framework authors and people who actually use them. So some of the things which are coming is that exposing CPU extensions critical to performance and enable running bigger models on the device and seamlessly interoperate with other web platform vendors, other browsers, and anything that's running inside the web. So some of the things that is happening and that's right now there. So let's start with compute extension. The WebAssembly spec as it stands only includes certain set of instructions that is exposed to the web. This is for good reason. We want to ensure the spec is concise and driven by application requirement. Now, relaxed SIMD is a feature that trades some of the portability by introducing local non-needed determinism in favor of performance closer to what you would see in hardware. This extension introduces WASM operations that can take advantage of hardware fused multiply and add integer dot products and several other instructions that speed up existing workloads. How much? it speeds up almost like 1.5 to 3 times. Uh, this is already part of almost all of your Chrome. This has been released for quite some time. So if you are running any application, you can actually take advantage of it. Now, precision operation. So remember when I started, I told that, okay, you have models with different kind of suffixes attached to it, FP16, 8, and all those. So a rule of thumb is that the bigger floating point or bigger that number you have is the model is bigger and better. But it's not always gonna be you. So the more bigger it is, the more bigger memory you need to actually load the model. Not always we need a complete full precision 16 or 32-bit models. So what you have now is that compared to single precision values, there are several advantages of using half precision values. So one of the huge part is reduced memory requirement, which in turn enables training and deploying of larger neural networks and reduced memory bandwidth, which speeds up data transfer operation, and which again speeds up math operation. So faster inference is what we get out of this. This is still in work in progress, but if you want to have a taste of it, you can actually enable it by going to your Chrome flags and finding the FP16 flag. Now, when pointers into WebAssembly's linear memory are currently represented as 32-bit integers. Now, this has two consequences. The heap sizes are limited to 4 gigabyte, and I'm pretty sure most of you have laptops or computers running much higher RAM than 4 gigabyte, right? So, if it is available, why can't we use it? So, application code that can target a bigger memory, WebAssembly has to be compatible with 32-bit pointer size to be accessible for that. So now there is a full working Chrome implementation that features this feature. So you can already try it in Chrome Canary, and I believe this is also available in Chrome Developer, like Chrome Dev versions, and Chrome Stable behind the flag. So everything we have talked till now, they have real tangible benefit when you want to run AI models. What are the benefits? The previous one, it lets you run much bigger model in a faster way. But you still might want to run a model big enough that has to be completely loaded into the RAM. And this actually enables you to access RAMs bigger than 4 gigabyte from your browser. Remember, when we started the talk, we told that what are the differences between running something in native code or running in your computer as natively and inside browser. These are some of the considerations and how you can kind of target that. Now, that's all nice and fine, but you also want to utilize the GPU compute. So another interesting programming model here is WebAssembly as the entry point for special purpose compute on the web. So we're using, you can say web GPU as a case study. WebAssembly can be used to bring native GPU applications to the web with same. So for example, if you have a C++ application for like even the whole Llama CPP. How many of you have heard about Llama CPP before? Just raise your hand. Okay, so Llama CPP is a open source project which lets you run most of the AI applications, like a lot of AI models, open AI models, uh, not open AI, sorry, open weight LLM models directly on your computer. It's a very nifty C++ program where it's a community project and it's hugely popular. You can just download it, and then you can download any of the LLM models from Hugging Face in specific formats like GGUF, and you will be able to run it on your own machine. I highly encourage you to just Google Llama CPP and you will find the project. It's very easy to run. And it runs all the LLMs on your own machine. Now, that's a C++ code. Essentially, there are projects where you can take the complete Llama CPP, convert it to WebAssembly, and run it directly from your browser without any change. So those are the kind of things web GPU enables you to do. So let's look at one of the asynchronous execution model. Now, the browser runs all the pieces of code sort of as an infinite loop by taking them from a queue one by one. So when some event is triggered, the browser queues the corresponding handler, and on the next loop of iteration, it's taken out from the queue and executed. This enables running multiple operations using only a single thread while still being responsive to other tasks. Why this is important? When you are visiting a web page, you are browsing a web page, you click a button, you don't want that web page to completely freeze up on you while it's executing it. So if you press that button and it's executing a LLM task in some backend, you don't want it to freeze. Previously, there were uh, web workers where you could actually just spawn multiple workers to do that. For specifically AI task and specifically compute task, we can have this asynchronous execution model, which also enables us very interesting scenarios like having agents directly on your web page. So one of the easy ways, not easy, one of the existing ways how we can integrate it is the JavaScript's promise integration. So JSPI is an API that bridges the gap between two programming models. So this is done by suspending the application when it issues a synchronous API call and resuming the application when the asynchronous input-output operation is completed. With JSPI, the application is transformed so that the synchronous operation in C++ are converted to web's asynchronous operation with very few changes to the application itself. Why it's needed? Because that WebAssembly code was a complete block. So we need to have asynchronous way of running that. This is a very simple example of computing Fibonacci using JSPI. Was under JSP origin trial. I believe it's still under trial, so has been trial for some time. So the two things I want to focus in the code are the masync chase that macro generates all the necessary glue code so that we can use JSPI to access the promises results, just like it would be for a normal function. The special command line option here is that is.jspi. This invokes the option to generate code that uses JSPI to interface with JavaScript import and return the promises. And there are great resources about it in Chrome's v8.dev, where they go in a lot of detail into JSPI and all the benefits. I just wanted to show a very quick example. Coming to memory control. So another surface that adds some friction when interacting with WebAssembly is that developers have very little control over the WebAssembly memory itself. The module owns its memory, and that isn't ideal because any API that needs to access to chunks of this memory will need to copy in and copy out. And depending on your application, this can really add up, specifically with a lot of, if you want to create some kind of chat or some kind of experience where it has to keep a memory. This memory control feature aims to provide a finer grained control over what WebAssembly linear memory can have and reduces the number of copies across the application pipeline. This is a very early stage feature and it's still on the prototype stage. Now, I've talked a lot about like the good things, then talk about the bad things. So these WebAssembly features, I want to set some of the expectations right as well. While CPU compute is everywhere, it isn't always the best option. You might not want to build an application which runs everywhere but runs bad for some users because they might not have the same CPU capability. So you should kind of build an application in a way where it can fall back on special purpose compute on the GPU, or if it is running in any other accelerator. For example, if it had access to NPU. So that makes it much better. So the right backend to use can be application framework or toolchain development or many factors influencing where you might get the best performance, model size, memory bandwidth, computing needs, etc. These are the considerations you need to take in account when you are starting to build applications using these and bigger AI models. This is not a caveat, or this was not a caveat till now when people were still using smaller models, or the target audience was probably not a low compute device. But with starting with huge models, and if you specifically target this for LLMs, a lot of computers start looking like a low resource device. So you have to be very careful about that. Now, let's talk a little bit about web GPU and what we are utilizing here. So, in the past year, web GPU has been launched in Chrome, and then after that, there have been a lot of very interesting demos and things people have tried. I'm gonna show some of them, not actually running them, but you can see the web page, so you all can try this right now in your machine and text back to me right now in chat if it doesn't work for you or if you have a problem. So what you see here is that it's a demo from MLC AI. So what they did was they're running a completely stable diffusion model directly on the browser. So what this means is that they're loading a complete stable diffusion. This was, if I'm not mistaken, stable diffusion 1.5, or they might have upgraded to 1.6. So you just load it. Once you load it, essentially, if you have gone online, offline, and still try to generate an image, it will generate an image directly on your computer without you having to install anything else. And it uses web GPU. And earlier this year, Google's MediaPipe team also published experimental support for this LLM inference. You can kind of try this also right now. I'm going to post the link as well in the chat. So this is also available again in the MediaPipe studio. If you go here, you should be able to run like a complete Gemma model directly on your browser and do an text inference. And this is not specifically Gemma, you can load your own model as well. And we will go to a like demo as well, how you can build something like this with your own models, not only Gemma. Now, coming to some other tasks. So this is Meta's SAM model, or segment anything, which essentially makes us do things like this, where if you want to build your own portrait mode in your phone or from any picture, this can segment anything. As the name suggests, this can segment any object from a picture. So this can enable you to build features where you can have a background blur, background dip, background replacement, things like background blur, which is running right now, all these. And this is also running in Hugging Face space, and you can actually try it in your own browser. So these are just a couple of the amazing projects which showcases the power of web GPU and AI. And there are a lot more like speech to text summarization. If you just Google, you will get a lot of them. So this is, but what about kind of performance, the result? So this is a little bit result of Hugging Face's web GPU test imaging benchmark, demonstrating tremendous speed up compared to a CPU implementation of the same model. Just for an example, on my own computer, web GPU was over 30 times faster for a equivalent code running in CPU. And a lot of people, as others have reported, web GPU accelerates the benchmark by over 120 times. This might vary based on your output, but yes. So what makes web GPU great for AI and machine learning is that web GPU supports compute shaders. So what are shaders? Compute shader is a program that runs on the GPU, taking advantage of the GPU's massively parallel computing abilities. That makes web GPU a very good match for machine learning because it's possible to run parallel array operation. Remember when we talk about tensors in the beginning, one of the three things we are going to exploit, this is the first thing, where that tensor has a huge number of data as like arrays, array operations, and on a lot of model, and WebGPU allows us to utilize that. And AI models often have billions of parameters. Among the numerous other improvements to web GPU in the past year, some of the things you will get, the two things is the 16-bit floating point and packed integer dot product. Why they matter? So remember, we hypothesized, or we told rather, recall that AI doesn't need a lot of precision. Shader F16 is a feature that enables use of floating point 16 type in web GPU shading language directly. This is a floating point type that takes up to 16 bits instead of the usual 32 bits. So half what we just talked. So F16 is smaller range and less precise, but for most, or rather I would say many machine learning models, this is sufficient. So you still have to check for you if it is sufficient or not, but almost most of the things people are doing in web, it is sufficient, including running LLMs to get good enough results. So Shader F16 helps in a few ways. It's quite similar to the benefits what we just explained in WebAssembly. Uh, so first, the tensors with F16 element take half the space, which cuts memory use in half. So GPU computations often are bottlenecked on GPU's memory bandwidth because your user might not have a very beefy GPU. So half memory can often mean shaders run twice as fast. The second benefit is that we do less compute by minimizing data conversion. Low precision data can be stored and then used directly without conversion. And lastly, A16 allows for more parallelism because there are fewer bits in the representation of F16. Most of the modern GPUs are able to fit more values simultaneously in the GPU's execution unit, which makes it run much faster and a number of like a greater number of parallel computation. So let's go back to Hugging Face's Stingstream benchmark from before. So if you see now with shader F16, web GPU now runs the benchmark even 3 times faster than floating point 32. So if you look at a more complete example, WebLLM is from the same MLC AI. You can again visit their website to run this. And again, we'll show how you can do that as well, but not using WebLLM. So it can run multiple large language models, but it does not use TensorFlow.js or MediaPipe as a backend. It uses something called Apache TVM. It's an open source machine learning compiler framework under the hood. What TVM does is that it literally runs a very small, lightweight WebAssembly VM, which takes any model and can run it. So, see, we have Rust like a planet trip to Paris using Llama 3 8 billion parameter model. On the left is the model with 32-bit quantization. On the right, 16-bit quantization. The 16-bit quantized model takes advantage of the shader F16. And let me go back and come again so that it runs again. Oh, it did not. Okay, so you will see how faster it is. So to use it, you still have to check if it supports or not, because it's an optional feature and not all GPUs have the same capability. Uh, an application has to first check if the GPU adapter supports this feature and if it is available, and explicitly enable it when requesting a new feature. Then in your web GPU shader, you will need to explicitly enable F16 at the top of the shader, and then you can just use it within the shader like any other floating data type. Now, what about quantization? What about even smaller? So many models will still work well with just 8 bits of precision, and that's very popular among specifically LLMs because they're by default very huge. Uh, and also with very a lot of other models like segmentation and object recognition. For example, a lot of segmentation models are not, it doesn't have to be that accurate. So for example, if I'm wearing this part might not need to be completely properly blurred maybe in your application. So you might be able to save, go for like from a 16 to 8 or 8 to 4 bit even quantization, just losing some accuracy. But there is still a problem. While shader F16 features enable use of 16-bit floats in the shader, very few or relatively few GPUs natively support 8-bit values. So not going down always isn't always good. This is where packed integer dot products come in. This is the second feature. This was already shipped in Chrome 123. And this, I think Intel was one of the large contributors to this. So modern GPUs have special instructions to take two 32-bit integers and interpret them as each four consecutive packed 4-bit, 8-bit integers, and compute the dot product between their products. This is particularly useful for AI and ML applications because matrix multiplication kernels used are composed of many dot products. And if you can make them faster, you make everything faster. Very small theoretical example. So multiplying a 4 into 8 matrix with a 8 into 1 vector. Computing this involves taking four dot products to calculate each of the values of the output vector A, B, C, and D. The process for computing each of these outputs is same, and before any computation, we first need to convert the 8-bit integer data to a type we can perform arithmetic with, like the F16. And then we'll do a element-wise multiplication, and finally add all the products together. In total, for the entire matrix vector multiplication, we perform 40 integer to float conversions and to unpack the data, and 32 float multiplications and 28 float additions. Now, with larger matrices, there are even more operations that needs to be performed. So how does packed integer is going to help us reduce this work? So packed dot products work on groups of four 8-bit integers, and we'll slice our data into groups of four to help visualize this. So for each of the outputs of the result vector, we perform two packed dot product operation using web GPU shading language built in .4u8 packed, and then add the results together. In total, the entire matrix vector multiplication, we don't perform any data conversion. We do 8 packed dot product and 4 integer addition. And we tested this packed integer product with data on variety of consumer GPUs, and compared with 16-bit floating point, you can see that 8-bit is 1.6 to 2.8 times faster. When we additionally use packed integer products, this is even more faster, almost 3 times, 1.7 to 3 times. How do you use it? You can again have to check, because like everything in web, not everybody has support of everything, and your users are essentially everybody on the planet. So you can check if the browser supports pack integer dot products by checking the WGS language feature property of the GPU object. Don't hate me for the name. It's not available in all browsers yet, but it's a core feature of the API. So the eventual implementations will all have it. All the browsers will have it. If the GPU doesn't natively support packed only dot product, then the browser falls back to the own implementation using polyfill. Uh, Small example how you can use it in a web GPU shader on the left is a sample web GPU shader which accumulates partial dot products into the variable sum. At the end of the loop, the sum will hold the full product between a vector and one row of the input matrix. On the right is the same shader written to use packed integer dot product. The main difference is that instead of loading four float values out of the vector and matrix, this shader loads a like single 32-bit integer. This 32-bit integer holds the data of four 8-bit integer values. And then we just call the dot for u pack to compute the dot product of the two values. So these are already shipped. 16-bit floating points is already available in Chrome, and it's gonna available when hardware supports it. And Chrome already implements packed integer dot products in all web GPU capable devices. You can already try it in Chrome stable. You don't have to go for Canary or any other things. So some of the proposed features is that what being worked on is what is called SIMD level parallelism to communicate or to perform collaboratively math operations like the sum over 16 numbers. It allows for a sort of cross-thread data sharing that should be very efficient. There is also a proposal on the standards group, and that's a prototype subgroup in Chrome behind an experimental flag. Here you have initial result to bring this to the stable, and we have some other proposals as well. So let's look at how this might speed up. So to evaluate the performance of subgroup operations in a real application, this implementation has an experimental support for subgroups in MediaPipe. This is tested against Chrome's prototype support for subgroup. This is GPU kernel is used for that, so that the language model is running there. So this is just the pre-fill stage. So this is running in an Intel GPU, and you can see the subgroups perform 2.5 times faster than the baseline. This is awesome, but also this is not consistent across all the GPUs. So still a cherry picked result. And here are some of the results applying these to matrix multiply micro benchmark. And this is actually tested on a lot of GPUs. So you will show that many of the GPU provides a massive speed up. They are 2, 5, even 13 times faster than baseline. However, notice that on the first GPU subgroups aren't much better at all. So that's the inconsistency. So GPU optimization is difficult. That's kind of the take out of all this, because using fancy GPU features doesn't always pay off what you might expect, because there are a lot of complex factors involved. The best optimization strategy on one GPU might not be best for others. That's why kind of falling back to use WebAssembly to get a persistent but might not be the best speed up is often recommended. You might want to minimize the amount of memory bandwidth, but also fully utilize the computational on GPU, all while staying under one register budget. These are some of the lot of considerations you might have to take. So just to iterate that point. So in this chart, we have taken some matrix multiply benchmarks from before, added another dimension to further demonstrate the impact. And this new technique is called Swizzle. Swizzle optimizes the memory access pattern to be more optimal for the hardware. You can see that the memory swizzle has a significant impact. It is sometimes even more impactful than subgroup. On GPU 6, Swizzle provides a 12x speedup, and subgroups provide a 13x speedup. Combined, they have an incredible speedup of 26x. So once these all proposals on all the problems are wrinkled out, we probably are going to look at awesome speedups on our consumer devices on browser. But then again, some of the GPUs, Swizzle and subgroups combined perform better than either one alone, but on other GPUs, exclusively using Swizzle performs the best. So take GPU optimization is difficult, but thankfully there are tremendous efforts and a lot of libraries are actually doing this work. So if you want to kind of go into it, I'd recommend some of the different libraries which utilizes a lot of this, and some of the demos I talked about. I'm going to post all those links into the chat. So if you are using any of these inference libraries and want to use some of these optimizations, just try to look at these. Now, coming back to caching and what you can do with it. So if you are serving an AI model right from your server, uh, it's important to configure the correct cache control header. But if you're uh, serving it from your own device, you also need to cache control it better way so that it doesn't load every time your user is changing it. So when the user reloads the page, the client sends a revalidation request, even though the server knows that the content is stable. Why this is important? Even though you are running the model from your user's machine, for the first time, the model has to be loaded either from the disk or from some server somewhere. So your user might have that model already available, which is not the use case for most people. But a lot of times the use case probably is you have built an application. For first time the user visits your web page, the model gets downloaded in the background or explicitly. And from the next time, the user should not need to again and again load that model. So when you serve an AI model, it's important to explicitly cache the model in the browser. This ensures the model data is readily available after a user reloads the app. You can choose one of the any of the following APIs to cache the models in the browser. For example, the cache API, the system API, and the IndexedDB API. So the general recommendation is to use the cache API, but yes. So with that, we're gonna go for a demo finally, and also a little bit, not too much, but a little bit into the code of if you want to do it, how you can do it. So let me stop sharing my page and load another page. How do I paste in? Share. So I'm gonna post the link so that you don't have to just look at my page and you can actually try it on your own machine. So I have pasted this link in chat. So if you want to play with it, you can just click that link. That should take you to this exact same page. So let me refresh the page. So I'm completely out. Okay, so since I had already run this once, this is cached model found in IndexedDB, which I don't want. So I'm gonna copy this link and I'm gonna open a incognito mode and load it again. Yes. And now if I try to run it, it will say load a model first. So either I can load a model from my disk. If I have the model, this one is running. I mean, you can check anything inside this, but I'm right now pointed towards CGMA 2B, GPU, and very small, supposedly 4-bit quantized model from Kaggle. So I'll just try to download the model from the web. So if you look at my network, which I show, refresh, download, no, yeah. So we'll just wait while it downloads. So what we're gonna do is that we'll first
Um, Looks like Ravimba blew his bandwidth. Um, we might just have to wait till he gets the model binary down.
Hello.
All right, looks like you're back. I think, um, yeah, it blew your bandwidth, probably.
Yeah, not bandwidth, probably the GPU bandwidth, but I don't see
Ah,
the sharing. The share screen button is disabled. What happened?
I'm not sure. Maybe it's because I'm screen sharing. Let me turn that
Oh,
off.
okay. Oh, yes, I can share now. So essentially, which page am I on? Okay. Yeah, so essentially, I just realized when I'm doing this, it cannot show you the Chrome like developer tools here, and I wanted you to show that. And the moment I stopped sharing, this one crashed. So okay, so it loaded everything, and if we do this, it's gonna generate a response hopefully. Okay, so it generated some response, and okay, so we have something which looks like a poem but not a poem. So this is how you can actually load, and if you see this is right now cached for my index.db, and if I reload the page, which I just did, and again, so it will always load it from cache, and you should be, uh, it doesn't show Chrome DevTools, but you should be able to see in DevTools as well. Now, if you want to do this, so you can actually play with the link I just gave you with the demo, but let's start looking at a little bit at the code. So since this is in glitch, so you should also be able to just open the code and fork it. So this is the glitch project. Uh, this one, if I press on preview pane, this is what we have here, right? So here are all the things we kind of talked about. How you can actually cache the model, how you can actually load it, how you can specify the duration. If you see, this is not anything specific to AI, specific to LLM. It's just how you normally have a LLM model, how you just cache it. And this is where we load the WebAssembly for our specific task, Chain AI. And here, how we will check if the model has been cached or not. So this is an example of how you can actually implement some of these. This is not model specific. Instead of Gemma, you can use any model you want. You can actually change that link, or you can just use that to load from your disk, or you can just build it with your own model or anything else. This is using MediaPipe as a backend. So when I say any model that is supported by MediaPipe, so that should be like you should be able to run easily with this. Now going back to our talk. So I kind of like to emphasize some of the key things we took away from this is AI inference right now is already available in web across devices, and it brings with it all the advantages of running on client-side devices, which are reduced server cost, lower latency, increased privacy. Also, as web developer or framework author, you can build a lot of these, and you can actually implement a lot of the performance tricks already. So one of the things to keep in mind is that web standards are fluid and evolving. So try out the experimental features, which is gonna eventually come to stable, but also keep a very close look on what is actually available right now in your stable browser for your audience, or what is in the experimental, so that you can already be ready to build on that. As you can experiment with these switches, please also provide feedback. These are feedbacks which goes to Chromium team, and if you have general feedback on WebAssembly at WebGPU spec, this is your time to get your voice in. What you want to see, what you don't want to see, what are the applications you are thinking about, what else can be done in this space to better support those applications. Because web right now, or your browser right now, is not just a place to see websites, it's completely kind of a platform which can serve you better. With that, I am gonna conclude my talk today. Thank you. If you want to get in touch with me, you can scan any of my QR codes available here. And I'll be also very happy to take questions asynchronously or hear anything you might prefer. Thank you.
Looks like we probably don't have questions. But yeah, thank you so much, Rabima, for taking the time out and doing this. This will go live on YouTube. So for anyone who joined late and wants to um, see the whole talk, you can go to the GDG Chapel Hill channel on YouTube and find the talk there once I upload it. And yeah, thank you everyone for attending. And we look forward to seeing you the next talk. If you do have some time, we would love to get your feedback on this talk at this link. Just click on it. I just posted it on the chat, or you can just visit tiny.cc/GDG feedback. Um, and yeah, that helps us make our events, future events, better. So yeah, please provide feedback, and also helps us know what kind of events or talks you're looking to get out of our Chapel Hill community. Yeah, and that's I guess that's all for tonight. Have a great weekend and be safe, y'all.
See you, everyone.